Right. This will be the last lecture of the series. Thank you for prevailing with me. Just let me make one or two remarks about the expression that is on the board that I had made. I had arrived at in the morning. I don't think I did justice to, I explained adequately as to how I arrived at this equation. One intermediate relation I would just like to mention, which can help you derive, is the fact that, at the reheating temperature, so what do you have? You have rho RE to be pi squared by 30 GRE TRE power 4, right? GRE is the number of relativistic degrees of freedom. And you have the other relation that rho RE is rho end, which you can relate to this V end that I had. It's the energy density at the end of inflation. And this is exponential minus 3 into, let me write it here, exponential minus 3 into 1 plus WRE NRE. Okay. You can arrive at relations such as this, the relation between TRE and NRE using expressions like this. Okay. So, and using those expressions, you can arrive at this result. The bottom line, I'm trying to repeat what I had said in the morning. The bottom line is that I have written this here as well. Okay. You combine these two to arrive at that. The bottom line is that, there was a question about what is T naught. You can estimate the wavelength or wave number associated with it. Okay. And that is known. Okay. And if you have a given inflationary model, right, and that just tells you about inflation, but you know what is rho end, right? And you will know HK, and from the observations, you know NS, right? And if you know NS, you know N subscript K, because NS will be related to NK if you look at the relations, okay? And from the form of the potential at the bottom, you know WRE, okay? So you can determine NRE. That's the point I was trying to make. And once you know that, okay, there is a simpler version of this without NK, okay? You should be able to arrive at that. And that will allow you to relate TRE, WRE, NRE, you can construct TRE from that, okay? That is the point I was trying to make towards the end of the last lecture. That was the whole point of this exercise. I will list references where you can turn to after the lectures. The last lecture, 12.2. I have my hands full in this lecture. Right. I'm supposed to discuss, evolution of primary gravitational waves. PBH formation. And generation of secondary gravitational waves. Clearly, this is an impossible task, okay? What is feasible for me to convey in a meaningful fashion in the 1 hour that I have is I will discuss enough details about this, and I'll provide you adequate details for you to fill in I'll give you enough information and you can fill in the details to get the spectrum today, spectra of primary gravitational waves today, and you can take the sensitivity curves of the various gravitational wave observatories, and then you can compare what scenarios are consistent with observations, what scenarios can lead to gravitational waves, primary gravitational waves of detectable densities. I will highlight a few essential aspects of PBH formation, and I will just write some equations, wave my hands, and tell you how to arrive at what happened, how secondary waves are generated, gravitational waves are generated. We are talking about what are known as scalar-induced gravitational waves, okay? And I have to give you some references to read to understand how the spectra are arrayed, okay? So let's turn to the evolution of primary gravitational waves. A new chalk. So we know the equation of motion. What do we have? HK double prime plus 2 script H, HK prime plus K square script HA. So we are interested in a mode of the gravitational wave. And if you recall, we have defined the primordial power spectrum, that is the tensor power spectrum generated at the end of inflation, to be 4 k cube by 2 pi squared into mod HK squared. And what we are going to assume is, let us consider the simple scenario where you have de Sitter inflation followed by radiation domination. This is what is of our interest. Okay. It so happens it's convenient to change my independent variable from this is, remember, this is conformal time coordinate. These derivatives denote conformal derivatives with respect to the conformal time coordinate. It is better to consider the scale factor itself as the independent variable. And I will let you work it out, okay? And we are going to assume scenarios where W is a constant. We're going to focus on scenarios W is a constant. Evidently, in de Sitter, W is a constant. So is in the case of radiation domination. And if we include epochs of reheating, we will include epochs where W is a constant, WRE that we just discussed. Now, let me open my notes to get my equations. Okay. So in de Sitter first, we need the solution. We have the solution. We will write it in terms of A. Okay. Remember, de Sitter is what do you have? You have HK eta. Okay. Okay, let me just rewrite this differential equation in terms of A that I will require. Just bear with me. Right. So you will find that the differential equation happens to be d square HK by dA square plus phi minus 3W dHK by dA plus okay, K square by 8 power 1 minus 3W into H squared. I hope that is correct. HK equal to 0. All right. Not capital A, small a. Okay. Okay. Something like this. Okay. Check this, please. All right. And so in de Sitter, you know the solution, right? Okay. I hope, there is I made an error here. It is divided by 2A. Okay. I'm just worried about constant. The factor is correct. Okay. I hope this is correct. In the case of, all right. We'll come to that. Okay. So you just need to, what I have done is that I have transformed this. I'm just worried about factors here. Let me just check that. Okay. A squared by A F squared. It's okay. I think it is fine. Okay. All right. Now in d zeta, the equation, the solution happens to be in terms of A. Remember, it was, I can write this as root 2 by MPL, right? 1 over root 2k, okay? 1 minus I by k eta, and eta in d zeta is plus 1 over AH, right? I'll call this as H naught or HI, okay? E power minus IK eta. Eta is, A is minus 1 over H eta. Therefore, eta is AH. AH. So that's fine. Okay. Eta is plus 1 over AHI. Okay. This is dimensionless. This is dimensionless. And there is a factor of 1 over A as well. This is what the solution is in d zeta. Let me confirm that. Yes. Okay. So I can pull out some factors. Let me write it differently. I can write this as root 2 by MPL. Okay. IHI by root 2 KQ. Okay. 1 minus IK by KE. Remember, I had introduced this K by KE. E power. Okay. No, this is, I will just not write it like this. It is 1 minus I by K by AH. E power IK by AH. A subscript I. Okay. HI being the Hubble scale during inflation. Okay. This is the solution. And this is in d zeta. Now we need to match this during radiation domination. Okay. And what we are going to do is as follows. We are going to consider scenarios, as I said, d zeta followed by radiation domination. Yes. Have I made a mistake? So it is 1 minus I k by A eta. Sorry, eta. This is I k by, yes. There is something wrong here. Okay. K eta. Eta is minus 1 over AH. All right. Eta is, no, 1 minus, sorry. 1 minus I by K eta, right? So this is minus I by IAH by K. By K. That's what it is, correct? Okay. All right. So now this is the d zeta solution, and you can evidently calculate HK DHK by DA, right? Okay. And we will need it at the end of inflation. All right. If you calculate at the end of inflation, maybe I should write it in the next board. Right. There are a couple of remarks I need to make. I will come to them. So I'm going to write this as HK at the end of inflation, eta E or AE, right? As some quantity, right? Okay, root 2 by MPL, okay? IHI by root 2 KQ. And then I can write this as 1 minus IK by KF, okay? E power IK by KF. What is KF? KF is A or KE. I've changed my notation. KE. KE is the mode that leaves at the end of inflation. It is AEHI. Is that clear? That is at the end of inflation. And you can calculate. Okay. So post-inflation, I'm going to denote this as A by AE. My variable, independent variable, is capital A, which is given by that expression. It's A by AE with respect to the scale factor at the end of inflation. In terms of this, I have checked this, okay? in terms of this happens to be dA squared 2A, okay? And then this is correct. K squared by KF squared A power 1 minus 3W. This expression is correct, okay? So you fix the earlier equation, okay? There was factor of AE which will be hanging around. Is that clear? This is essentially my differential equation governing the tensor modes, okay? And I have defined this convenient variable to be capital A to be A by AE. And now I need, so I'm going to post-inflation, I'm going to write my HK eta as HKP, which is primordial times chi k of eta. Okay. Sorry? KF, I keep KE. Is that clear? Okay. I've changed my notation from the paper. Okay. So KE is the mode that leaves at the end of inflation. All right. And this equation is correct, equal to 0. The earlier equation, there may be factors which may be missing. Okay. Check. Please check that. And we know the solutions in D sitter, right? And we know what is its value at the end, and that's what leads to the standard PT of K, which I didn't write. I will write soon. Okay, and I'm going to write it in this fashion. What it means is that my chi K at I should write this as A post inflation, right? Post inflation. This is how I'm going to write. So chi K A equal to 1 is equal to 1. Is that fine? Okay. And what you can also show is the following. You can show that from this solution, you can show that d chi k by dA, all right, at A equal to 1, that is at the end of inflation, is minus k by ke whole square divided by 1 minus k by k. Okay. And this is 0 for k, say less than or equal to 10 minus 2 Ke. Okay, roughly 0. Is that clear? This is not surprising. On super Hubble scales that I didn't emphasize this point, okay? Just like the curvature perturbations, the tensor perturbations, freeze on super Hubble scales, all right? Other than those modes which have hardly had enough time, to evolve on super Hubble scales. So what do we have? We are in this situation that I have been drawing repeatedly. You have inflation and you have radiation domination. You have modes leaving, and this is Ke. Okay, this is of course N. Okay, and this is log of lambda P and DH that we have been plotting so many times now. Okay, inflation, radiation domination. Okay, and this mode is Ke. Correct? And these modes have hardly had time to freeze on super Hubble scales. Okay, and so we are going to not quite going to go close to Ke. You can do that if you want. Maybe you have to do it numerically to pick up the behavior towards the end of inflation. Okay, but we are going to remain a little further from Ke so that the derivative is almost 0. Okay, you can take into account that derivative and calculate as well, but we have assumed derivative to be 0. And the other point I need to mention is that we are going to focus on scales such that K is reasonably larger than KEQ. Okay? That's right. K is much greater than KEQ. So what does this mean? All these modes re-enter during the radiation dominated era. Okay? This is what I'm going to assume for throughout this lecture, whether it is primary gravitational waves, PBH, or whatever I'm going to cover thereafter. Okay? All right? So, and we are going to assume instantaneous reheating. Okay, instantaneous reheating. So all I need to do is that, I need to solve for this in the radiation dominated epoch, okay, and match the modes. That's all I need to do, okay. And what I'm going to do is that these modes are going to re-enter the Hubble radius at some point in time, right, at some point in time. And what is going to happen is that I'm going to evaluate the spectrum at late times during radiation domination, okay. I'll consider a scenario when K times A is capital A is much greater than 1. Okay, so I can erase this. I know this solution, right? Okay. So what do I going to assume? I'm going to consider Ka to be much, much greater than 1. What does this imply? These modes are well inside the Hubble radius. Okay. And I'm going to consider them, say, close to the epoch of equality or something, because beyond that, it's not radiation domination. Okay. And what we will see is that these are modes that correspond to these tensor perturbations or gravitational waves. Okay. When they are inside the Hubble radius, gravitational waves, the energy density will go as 1 over a power 4. Okay. And you know that the energy density of radiation goes as 1 over a power 4. So once I evaluate the rho GW, I will write down the expression for rho GW. Okay. And once I evaluate that, I will divide it with respect to radiation domination. Sorry, energy density of radiation. In other words, I can express the rho GW in terms of energy density of radiation. So in other words, the energy density of gravitational waves today, right, can in terms of the energy density of radiation today, barring some factors which will depend on the dynamics, dynamics of the early universe. Okay, so let's go through the algebra. Okay, so this, as I said, this equation is exact. And again, to remember, capital A is A by AE at the end of inflation. Capital A is 1. Okay, and we are going to impose these initial conditions, right? So notice chi k at capital A equal to 1 is 1 because I've absorbed this HP. Okay, in fact, what is PT? Tensor power spectrum at the end of inflation at A equal to 1, right? This is essentially K cubed by 2 pi squared, okay? 4, I think a factor of 4, okay? Into mod HP squared, KP squared. This is what I have said. And this is, you know what it is. It is 2HI squared by pi square MPL squared. This is what it is. Okay, and this number is like 10 power minus 10 or so, right? If R is 0.1, this number is like 10 power minus 10. Now, what is that we want to calculate? Firstly, we want to solve for the modes, and I'm just going to erase this equation because, okay, maybe I don't need to erase that now. I can erase that part. Okay, let me see. Okay, so I'm interested in the energy density of gravitational waves in a given mode. Okay, and I want to evaluate at eta naught, which is today. All right, so this is what I'm interested. So let me define a few quantities. That is the expression I'm seeking. Okay, so this happens to be, right, MPL squared. I'm going to K cube by 2 pi squared. Okay, mod H K P whole squared. Okay, into not, this is what we will need, but I'm writing at any given time eta. Okay, into half chi K prime eta squared plus K squared by 2 pi K eta mod squared. All right. This is the energy density. All right. And this is nothing but, okay, you can write this entire expression as nothing but, okay, MPL squared by A squared PT of A. This is the primordial tensor perturbation spectrum, right? Okay. So essentially, I've left a lot of steps. What we have done is that we have actually considered quantized gravitational waves. And we have evaluated the expectation value of the energy density in a given mode, okay, of the tensor perturbations in the Bunch-Davies vacuum. Okay, that is what we have done. So this is often referred to as the spectral density of gravitational waves. If I integrate over all K, right? Okay, if I integrate over all K, I will get the total energy density, all right? But I am not integrating over all K, I'm looking at 1K, okay? Right. Okay. And now this, for instance, I mentioned that we want to evaluate this deep inside the radiation dominated era. Okay. So I need to solve for this in the radiation dominated era. In the radiation dominated era, what is W? It is 1/3. Okay. So this becomes 4 by 2a. Okay. And you can easily solve for this. In fact, it is better to solve the Mukhanov-Sasaki equation in terms of conformal time. It's trivial. But here also you can solve for it. And I'm just going to write down the solution. Okay, so keep this in mind. So we are interested in modes which are a couple of orders of magnitude smaller than the mode that leaves at the end of inflation. This is to avoid effects due to late time, effects at the late stages of inflation as epsilon1, starts deviating largely from very small values in slow roll inflation. Otherwise, my spectrum will not be correct, the primordial tensor power spectrum. Okay, and we are assuming on super Hubble scales, this derivative is 0, its amplitude is unity. Okay, so what you find is that you can quickly solve for chi k during the radiation dominated era. Okay, and it's given by this expression. Ek e power minus I k by KRE. Okay, I will explain what is KRE is, just bear with me. Okay, into A by ARE minus 1, okay, plus FK into E power IK by KRE. Shouldn't have erased that, A by ARE minus 1. Okay. All right. So what I'm assuming is the following. I'm assuming here, the way I have written to allow for later discussion, I've allowed an epoch of reheating. Okay. You need to replace ARE by capital A at the end of inflation, which is 1. Okay. And KRE by KE. Okay. That's all. This is to permit me to discuss reheating later. Okay. Now, I hope you understand. I have obtained the solution, and it's a matter of determining EK and FK. Okay. Now, there is some algebra involved. I can refer you to papers where this is calculated. Remember, I'm interested in calculating this. I have written in terms of eta, but I'm going to write in terms of capital A. I'm interested in a domain where it is, it's well inside the Hubble radius towards the late stages of radiation domination. And what you find is that you can obtain rho GW in this limit, comma K eta to be MPL square by 4 AF square A power 4 PT of K into mod EK squared plus mod FK squared. That's what it is. Sorry? Oh, it's AE. Yes. AE squared. Right. That's right. This is what you obtain. Okay. Now, what I am interested in, omega GW of K eta. What is omega GW of K eta? It is rho GW of K comma eta divided by rho critical, which is 3h squared MPL squared. This is h squared during the radiation domination. Okay. So this happens to be, all right, I will write it here. This is, I can write this as essentially, okay, I will write it as KRE squared, ARE squared divided by 48 AE squared, H squared capital A power 4 Pt of K into mod E. Okay. I have written another quantity. I will write the relation. Okay. I will write the relation between these two quantities in a matter of minutes. Okay. Into this. All right. And but what essentially happens is that, so if you had de sitter, reheating, and radiation domination, right? What will happen is that I have to match them here. I have to solve for the modes and match them here. Okay, I'll squash this epoch very soon. Okay, I have written in terms of KRE and capital ARE. Okay, and they are given by these conditions, right? During radiation domination, H squared A power 4 is HRE squared ARE power 4. I hope that is clear. It just implies that during radiation domination, H squared goes as 1 over A power 4, right? Capital A is small a, so H squared is proportional to A power 4. Now, you find that, therefore, what happens, and KRE is ARE HRE. Okay? So, what happens is that, this gets cancelled, all right? And as a result, you have a simple version. I have to erase this, okay, for want of space. I'm left with this expression, okay, omega GW. I haven't yet said what is script EK and FK. I will mention that, just bear with me. It is just some version of EK and BK. So omega GW, eta is, you can d by K by, right, 48, okay, mod EK squared plus mod script FK squared. Okay, right. So, okay, let me explain what I have done again. I have just calculated, I can calculate rho G K eta during radiation domination. During radiation domination, this is the solution. Whether it's instantaneous reheating or there is an epoch of reheating, that is going to change this AK and FK. It's just going to change the conditions on chi. Okay? And so using this solution, I can construct rho GW, omega GW during the radiation dominated epoch, at late times during the radiation dominated epoch. And it has this structure. Now I have to tell you what is, it is just EK. This is the relation between, I'm writing it for the sake of completeness, by 2 KRE by K script EK, and FK is similarly minus I ARE by 2 KRE by K script F. All right. Now what's going to happen? If I have instantaneous reheating, right? Okay. In the case of instantaneous reheating, what do I have? I have ARE reduces to 1, okay? And you can match these, right? You can match this mode to the de sitter mode and immediately determine script EK and script FK, and they happen to be the following. Script EK is 1 minus 2I K by KE minus 2 K square by KE square. This is, 1 minus I K by KE. This is an exact match. I haven't taken it to 0, the derivative to be 0, okay? And then what you obtain, FK to be 1 over 1 minus I into K by KE. This is what it is. Now, in the limit K much smaller than KE, what do you see? You see that EK and FK tends to 1. This goes away, this goes away, this goes away, this goes away, and both EK and FK are 1. Okay, so what it means is that in the case of instantaneous reheating, where I have a de Sitter universe followed by radiation domination, okay, the primordial spectrum remains the same. Okay, this is the bottom line. Okay, and I'm going to again quickly wave my hands to arrive at this is arrived at the end of no, not at the end of inflation, close to at the end of the epoch of radiation domination, towards the late times during radiation domination. Okay, now if you want it today, omega GW today, right? What you see is that, okay, what you see is that omega rho GW, as you can see, right? Rho GW, you can see here, these are all K dependent quantities. This goes as a power 4. Rho GW, okay, K comma eta goes as 1 over a power 4, right? But we know rho radiation goes as 1 over a power 4. Okay, so if I calculate the quantity, so in other words, rho GW K comma eta divided by, all right, rho radiation at any time is equal to rho GW naught as a function of K divided by rho radiation naught today. Okay, so what it means is that, you know, I can write rho GW K comma eta in this fashion. Okay, and now what happens is as follows. This is rho R of eta, right? Okay, now what happens is that if I divide during rho total during radiation domination and rho total during radiation domination, right? Okay, what do I have? What is this quantity here? This is of order unity. Okay, because during radiation domination, the total is just due to radiation. So this is of order unity. So what you can see is that, okay, this is what? This is omega GW K eta, K comma eta. Okay, I can write this as omega GW if I, you know, at K, if I multiply by, you know, rho C naught. Okay, so if I write, you know, I'm sorry. No, there is something not quite rho total. No, there is. If I divide this, I will get this result. Sorry. That's correct. That's correct. Okay. I want the other relation. I want, okay. So I can divide this by rho C naught. Okay. I'm sorry about, okay, rho C naught. What do I want? I want this guy. I don't want this. Okay. So essentially, modulo, you know, factors. What is this? This is omega R naught. And this is my quantity of interest. So omega GW naught as a function of K, I can multiply by x squared, okay, is, okay, I'm missing various factors, omega and R naught h squared into omega GW K comma eta. What I've been careless about is factors involving G, R, E, G, and so on, okay? The fact that G changes, you know, this is not quite true. It doesn't quite go as just 1 over a power 4 because factors of G change. I need to account for that from early times to late times. But this expression is correct. This expression is largely correct, modulo overall factors which involve G, okay? The number of relativistic degrees of freedom. So let's estimate what should be omega G naught K today, okay? Omega G naught K h squared. What is omega R naught h squared? We have seen this. We have calculated this. If you allow only for, you know, whether you allow for only photons or you account for neutrinos, it's just something like 2.48 into 10 power minus 5 or some 4.1 into 10 power minus 5. So it's 10 power minus 5. Okay. Now, what is this guy? This is, we saw, it's like 10 power minus 10 or so. Okay. And then there is a factor of 48, etc. So essentially, what you find is that it's 10 power minus 5, something like 10 power minus 11, 10 power minus 12. So this is 10 power minus 17. Is that clear? So if I had, okay, I'm sorry about this messy blackboard. let me clean it up and indicate. Indicate what we have done. Okay, so we have to do this. We would like to do this. De-sitter, reheating, radiation domination. And you know what I have done post that epoch. So I just need to evolve the gravitational wave until late stages during reheating. And what I have shown is that in the part I have erased, remember, all the previous dynamics is buried in just those coefficients Ek and Fk. Nothing more. Okay. And they are, obtained by matching whatever happened in the earlier epoch. You can even mess up with your dynamics here. Okay. You can introduce multiple stages of reheating and so on. Okay. And they will essentially affect Ek and Fk. But at late stages, when the modes are inside the Hubble radius, we saw it goes as 1 over a power 4. Radiation also goes as 1 over a power 4. Therefore, I should be able to express omega GW today in terms of energy density of radiation. That's what I have done. And this is largely true modulo factors of, G. Okay. And what you find is that omega GW h squared today at a given K is omega R naught h squared times this omega G K eta, which is evaluated at late times, which is given by this expression. Okay. And again, I'm repeating, the script Ek and script Fk are related to Ek and Fk, and they determine what happened prior to that. And what are the modes we are interested in? We are interested in K, something like, KEQ to KE. So let us say 10 power 2 KEQ to KE by 10 power, something like this. Okay, so that you are away from modes which are close to entering radiation domination, and you're away modes, that are leaving at the end of inflation. So that late time effects as the transition from radiation domination to matter domination occurs are not affecting your spectrum, and late time effects during inflation are not affecting the shape of your spectrum. What you essentially find is the following. Okay, if you plot omega GW, okay, as a function of K, it is plotted often as a function of F. And I will leave this as an exercise for you to do. What you can show is that, I will write it here. F is K by 2 pi. You can show that this is 1.55 into 10 power minus 15 K by 1 megaparsec inverse Hertz. Okay. If K is 1 megaparsec inverse, it's about 10 power minus 15 Hertz. 1 megaparsec inverse is, CMB, close to CMB scales. Okay. That's 10 power minus 15 Hertz. Okay. LIGO observes at, tens of Hertz. Okay. To a couple of thousand Hertz, if I'm right. Okay. So what you essentially have is a nearly scale invariant spectrum, which is at 10 power omega GW h squared is 10 power minus 17. Okay. And over any frequency which is small. Okay. That's what you have. Now, I am literally out of time. Okay. So I'm just going to say what you need to do. I erased a differential equation for chi in terms of capital A. Okay. Chi k was my dependent variable. Capital A was my independent variable. You can now introduce this epoch of reheating. Okay. And what will you have? You know the modes at the end of inflation. You know the mode and its derivative. You know the mode at this point, which is written in terms of some Ek and Fk, right? And you will have solutions here, and they can be obtained in terms of Bessel functions. Okay, they can be obtained in terms of Bessel functions. So you'll have two solutions. So there'll be two constants here, very much like the ultra slow roll, mode matching that we had in the ultra slow roll inflationary model that we discussed yesterday. There are three phases. Okay, you know the initial solution, which is de-sitter. and there is an epoch of reheating. Let us say you have CK and DK, and you have EK and FK. Okay, you can match these here and match these here and calculate the spectrum. So what do you have? You have here, let us say this is KE. Okay, KE can be something like, as we said yesterday, 10 power 19, 10 power 20 megaparsec inverse. Okay, so that corresponds to how much? Okay, this is, if you multiply this by 10 power 20, you're talking about 10 power 5 hertz. Okay, 10 power 4, 10 power 5 hertz. Okay, and that's much beyond any of the observatories today, but there are observatories that are being proposed. Okay, and then there'll be another scale. What is that scale? What will be the other scale? That's the scale which corresponds to KRE. Okay, I need to draw it here. I'm going to erase this. This result remains the same. It is just that because of the dynamics in between, script AK or EK and FK are now different. So what are we interested in? We are interested in this picture, right? Oops. So I have an epoch of some domination, and I should plot it like this. This always have difficulty like that. That is supposed to be. So this is KE, right? This is KRE. This is reheating, and this is, N equal to log A, and this is your logarithm of lambda P and the Hubble radius is what you have. Okay, so this mode is your KRE. It leaves the Hubble radius at an earlier epoch, not surprising. It is less than KE. Okay, and this is the epoch of radiation domination. Okay, and so there is a window here, window of modes between yes, that's correct. This is, okay, KE leaves at the end of inflation. KRE leaves at an earlier epoch. Okay, this is not right to point here. This mode is KRE. This is KE. And this wavelength or wave number is KRE. And KRE is smaller than KE. So that is KE, and this corresponds to KRE. Okay, over this epoch, okay, there will be an effect of the epoch of reheating. What you can show is that, okay, you can show that the epoch, all it does is that it introduces a tilt in this omega g spectral density of gravitational waves, and the tilt is given by this expression. Just give me a minute. It's given by, it is k power ngw, omega gw is proportional to ngw, where ngw is, I need some more room to write, 2 into minus 2. Oh God. WRE by 1 plus 3 WRE. Okay. All right. So let's understand what happens when WRE is 1/3, NGW is 0. So instantaneous reheating corresponds to a case where you have a scale invariant spectrum. And when WRE equal to 0, like if you have an M squared phi squared model, what happens to this? WRE equal to 0, it is minus 2. So what will happen is that after KRE, the spectrum will start coming down like that. Is that clear? And when WRE is plus 1, that's the other extreme. Okay, that's the maximum possible value. If you have scalar field driven inflation, that is, what is W? Scalar field driven reheating. Okay, W is P by rho. P is phi dot squared minus V by phi dot squared by 2 plus V. So one extreme is when the potential dominates, when W is minus 1. Okay, and the other extreme is W equal to plus 1 when the kinetic energy dominates. At the bottom of the potential, you imagine a situation where the kinetic energy dominates. You have what is known as a stiff equation of state. W will be +1. When W equal to +1, what does this become? -2 into, this is -2 divided by 4, which is 1. So it has a tilt, which is like this. It has to be smaller than this. It is like this. And you can make that blue tilt, possibly, depending, you can pull your KRE early so that it goes through the sensitivity curves of the various gravity wave observatories. Or you can do one more thing, okay? There is nothing that stops you from doing this, okay? The epoch of equality, I'll leave it untouched, okay? There is radiation domination. So I have radiation, this I have written in an enlarged, drawn in an enlarged fashion. So I have an epoch of reheating, right? Let us say I have radiation domination, and then there is another secondary reheating phase, and then there is radiation domination, and there is equality. So what will it do? Okay, you can have a situation. I will draw this. So you have this thing. If let us say I have stiff equation here. Okay, so which means that it will rise earlier. Okay, and then if it is radiation domination, it will be like this and it will fall down. Okay. If this was, W equal to 0, W equal to 1, WRE, I mean. Okay. So this is, omega GW h square as a function of K. Is that clear? Okay. So this corresponds to modes that leaves earlier. Okay. So they are affected by so this is where W equal to 1. This is W equal to 0. Okay, WRE. All right. And here it is -2. Okay. So this will be KR. This will be KE. Right. KE. Okay. And, so there are two. What do I have? Okay. So this is KE. All right. There are two scales here. Okay. No, there are scales that correspond to that re-enter at this scale. No, just a minute. This is the mode that re-enters at the end of the first reheating phase. In the original case, there was only one reheating scenario. Okay, so there will be modes that enter at the end of the first reheating phase and mode that re-enters at the end of the second reheating phase. Yeah, okay. So you can have scenarios which in some sense enhances the spectrum of primary gravitational waves. And of course, I have modeled with simple WRE. You can make a scalar field do various things, and they can have, in principle, more complex spectrum. So now, with that, I complete discussion of primary gravitational waves. Okay. I think secondary gravitational waves are strictly out of the window now. So in the remaining whatever time I have, I will just outline how you calculate the extent of PBHs that are formed, if you have enhanced power on small scales. In that, if you don't have enhanced power, I've already indicated how the amount of PBHs formed are incredibly small. Okay, and we want this enhanced power on small scales. Yesterday, I discussed a scenario of slow roll, ultra slow roll, and fast roll. Okay, fast roll is required to lead to the end of inflation. Scenarios that can lead to enhanced power on sufficiently small scales in the primordial power spectrum. I will just illustrate as to, I will just very quickly outline how to calculate the extent of PBHs produced in this case. Well, it applies to any spectrum. It is these spectra which lead to adequate number of PBHs. So let's discuss a few essentials. I need to open another file, just bear with me. So we are going to assume the simple scenario of inflation followed by radiation domination. We are going to have instantaneous reheating. And again, So inflation followed by radiation domination. And we are going to focus on scales where K is much, much larger than KEQ. Remember, this is like 10 power minus 2 megaparsec inverse. All right. And what are we interested in? I'm going to draw this picture again. Okay. Log of lambda P dH, right? And you have inflation and you have an epoch of radiation domination. And what we have in mind is as follows. There is a mode with enhanced perturbation with PS, let us say 10 power minus 1 or 10 power minus 2 or so, okay, that re-entering the Hubble radius. What we are imagining is this enhanced perturbation just collapses to form a primordial black hole instantaneously, okay? And just a few assumptions. What is the mass of this? We need to, of course, estimate how many black holes, such black holes, and what are the masses of these black holes, etc. Let's make a few estimates which are easy to do. Okay. Okay. So okay. They enter some mode K, re-enters the Hubble radius with an enormous amplitude for the perturbation, right? But still less than 1, so that perturbation theory remains valid. And the whole mass, forms, goes on to mass within the Hubble radius, goes on to form the black hole, barring a constant gamma, some constant of order unity, which may depend on the details, etc. And what is MH? MH is the mass within the Hubble radius. Okay. And what is that? That is just gamma times 4 pi by 3. Okay. H minus 3, right? The Hubble radius is H times rho. Okay. But rho, I can use the Friedmann equation, 4 pi by 3, H minus 3. What is rho? Rho is 8 pi by, rho is 3h squared MPL squared, right? So this becomes H minus 1, 3 goes away, okay? And I'm left with 4 pi gamma, 4 pi MPL squared, MPL squared H inverse. This is the mass of this black hole that is supposed to form. And I'm going to compare with MEQ because I know what is it exactly. And evidently, that is just, if I don't worry about the gamma, if I just ask what is that is the mass of the black hole. There is some uncertainty in the overall mass, okay? And that is captured in this constant gamma. And then otherwise, the mass within the Hubble radius collapses to form a black hole. And MEQ is just, as you can imagine, is just 4 pi MPL squared HEQ inverse. And I'm going to use the subscript K to denote that this is HK at re-entry, not at exit. Okay? All right. Therefore, what do you have? M by MEQ happens to be, right? Okay, is equal to H. MEQ is HEQ inverse, so it is gamma times HEQ by HK. That's what it is, right? And I'm just going to do a few things, all right? And this is during radiation domination, okay? So modulo factors of G, okay? I'm ignoring factors of G, right? And that can be inserted, carefully. And some of the papers will contain all the details, okay? I will share the references. I'm going to ignore factors of G so that we get the overall dependence. So what is HEQ? This is gamma, okay? I'm going to say proportional to hereafter because I can even drop the gamma for that matter. HEQ is, this is AK squared by AQQ squared. Why? Because we are in a radiation dominated epoch, right? Okay. Now what do I have? Let me erase this. Please keep this picture in mind. All right. Now what do I have? So M by Mk by Meq is proportional to AK squared by AEQ squared. I'm going to multiply K squared by KEQ squared. Okay. And I'm just multiplying by dividing by the same quantity. Okay. So this becomes, right? But K is AKHK, right? So this becomes AK squared HK squared divided by AEQ squared HEQ squared, right? KEQ squared by K squared. Okay. All right. Now this is a quantity of order unity. Why? Because during radiation domination, H modulo factors of G goes like, H goes as like 1 over A squared. So until equality, this should be true. So what we have shown is essentially Mk, the mass of the black hole, is inversely proportional to K minus 2. Okay. This is something we will require. Okay. There are constants involved. I am not even writing them because for want of time, but this is the argument essentially. Now, let me do one more thing. Okay. Let me discuss, the formation of black holes. So what have we said? We have said that the mass inside the Hubble radius, when it enters with a significant perturbation, collapses to form black holes. And what I have shown essentially is that M is proportional to K minus 2. Okay. I will use this result later. So delta is the perturbation in the energy density, delta rho by rho. Okay. And one assumes that the perturbations are described by a Gaussian distribution of the following type: 1 over 2 pi sigma squared e power minus delta squared by 2 sigma squared. I will explain what sigma square is. Okay. And beta is the fraction of energy density, of the total energy density that goes on to form black holes. Okay. And that's given by integral d delta p of delta. Okay. Now, what happens is that not all densities go on to form black holes. There is a critical density. Okay. Right. Up to some large value goes on to form black holes. I hope it's clear. They enter, there is a density perturbation, which is characterized by the delta, which is delta rho by rho. Okay. And there is a probability of this density perturbation, which we are assuming to be Gaussian. If there are non-Gaussian, that has to be accounted for. We are assuming it to be Gaussian, which is what is done in the simplest of what is known as the Preschecter formalism. Okay. And if you carry out this integral, it's given by this expression: 1 over 2 error function, 1 minus this guy, the special function of delta C divided by root 2 sigma square. Okay, this is an integral, you can check it out. Now, what is the sigma square? Right? The sigma square is a function of R. Okay, I will very quickly clarify what the scale R is. Okay, it's defined as, it's the variance, okay, dk by k, all right, p delta of k, right? This p delta is different from this p delta. This is the probability of the density perturbation. This p delta is the power spectrum. Okay, p delta of k. Okay, that is p of delta. This is p subscript delta. It should be clear. Okay, and there is a window function. This is the power spectrum associated with the density, what is known as the density contrast, delta rho by rho. Okay, and that in turn is related to the primordial scalar power spectrum, which we have defined. We need to obtain that relation. I will try to explain that relation in a matter of minutes. And this W is some window function. So what do you have? You have density perturbations, which were generated from during inflation, and they have evolved and caused a density perturbation, a density contrast. Okay, and this is what is the sigma square is defined as. Okay, and what else? And this WK of R is a window function. There are different types of window function. What people often assume is a Gaussian window function by 2. Okay, so what are you supposed to do? This will be related to the primordial scalar power spectrum. I will explain how that is related in a matter of minutes. Okay, and once you give the primordial power spectrum, okay, you calculate this. This is from 0 to infinity. Okay, you calculate the sigma square of R, plug it in this. Okay, and you obtain beta, as you can imagine, as a function of R. Okay, R is some smoothing scale, over which you are estimating the sigma square of R. Okay, there are only 2 scales here. Okay, well, there are 3 scales here, K, R, and M. We will see what the relation is. We have already seen the relation between M and K. M is the mass of the black hole, M subscript K, and we saw that it is related to, M is related to K minus 2 or K plus 2. Okay, M is K minus 2. Okay, so I need to relate R to M. But there is only one scale, which is K is like R. So I will eventually set, I'm sorry, K is R inverse. I eventually said that, K to be R inverse later. But let me clarify a few points about this P delta of K. Okay, how do I arrive at this? Okay, so well, you go to the Einstein's equations, and if you ignore the first term, the 0th Einstein's equation, okay, and there would be a 3h phi dot plus phi dot plus h phi, okay, and then a grad squared phi equal to 4 pi g a squared delta rho. That's what you will have, okay, and the other 2 terms can be neglected because phi dot is on. We are on super Hubble scales as the modes are about to enter the Hubble radius. Okay, the other terms can be neglected in this limit. Phi dot, for instance, vanishes. And what we are interested in, delta rho by rho, I divide by rho, okay? And this is delta rho. I'm sorry, this is delta. And I can, talk in terms of in Fourier space, though, so this becomes K squared. I'm not worried about the minus sign, okay? We will see that P of delta will contain mod delta K squared, so I don't worry about this. So delta subscript K, this is subscript K. And now what do I have? Rho is what? Help me. 3h squared by 8 pi g. Okay, there is a factor of 2. This goes away. So what am I left with? I'm left with K squared phi K equal to, help me, 3 by 2. Okay, K squared by A squared H squared is 3 by 2 delta K. Okay, that's what I want. Okay, our delta K equal to 2 by 3 times this guy. And as you can imagine, P delta K is what? K cubed by 2 pi squared mod delta K squared. Okay, so what do you get? Okay, you get the following. Okay, you get this to be K cubed by 2 pi squared, right? 2 by 3 whole squared, right? Okay, K by AH power 4 times mod phi K squared. Okay, and there is another relation which we have already obtained. If you recall, if you look at your notes, there is a relation between the curvature perturbation and the Bardian potential. Okay, on super Hubble scales, when they are in a universe driven by an equation of state parameter W, And for W, we had this expression is W plus 5 divided by 3 times W plus 1 times 5K. Okay. In radiation domination, what is this? RK equal to 6 by 4. Okay, which is 3 by 2 5K. Or 5K is, so I have this relation, which you will see being used regularly. 2 by 3 whole power 4. Okay. And then K by AH whole power 4. K cube by 2 pi square. Okay. Mod RK square, which is nothing but PS of K. This is 16 by 81. That's it. Okay. So what we have is P delta of K from my primordial power spectrum. So if you have this power spectrum, that I can take this guy and substitute that. Okay. So I have that expression and calculate sigma R squared. Okay. Sigma squared of R. Okay. So, and what you need to calculate? You calculate sigma square and then go and substitute in beta. I'm going to take about 5 to 6 minutes and wind up the discussion with PBHS. Okay. Please bear with me. I hope it is clear. You calculate sigma square of R. Where is the primordial spectrum buried? This ultra slow roll inflationary model that is buried in here. This is your primordial scalar power spectrum. You substitute that and you will get a sigma square as a function of R. Okay. You plug that in beta of M. Okay. Beta of M tells you the fraction of the total density that has gone on to form black holes of mass M. Now, in the absence of any other scale, what is usually done is that you choose K to be R inverse. Okay, wherever you see, you choose K to be R inverse. What it implies is that, this R is the smoothing scale. That's not the curvature perturbation. Okay, that's the smoothing scale. All right. And that leads you to the relation. So what do you have? M is proportional to, let me write this here. M is proportional to K minus 2, right? That's what we obtain, which means it is proportional to R squared, or R is proportional to M power half. All the factors included, etc., will be, can be found in one of the references I will share eventually. Okay. So let me summarize again. You are given a power spectrum. You know what is P delta of K. That is given by this expression. It's just K power 4 times this guy. Now take that and calculate sigma square of R. Take that sigma square of R and plug it in beta of R to obtain beta of R. Okay. And you can express R in terms of M to obtain beta of M. What is beta of M? It's the fraction of the total density that has gone on to form black holes. Now, what is this FPBH of M that people talk about? Okay, so let me get my notes. This happens to be essentially, right? I'm going to include a knot. Okay, this is something evaluated today. What is this FPBH of knot of M? This is essentially the total amount of PBHs today, all right? There is a M that I'm suppressing the dependence, okay, in the form of cold dark matter today. This is what we are interested in, okay? And that is nothing but rho PBH naught. Again, I'm just going to miss out factors of G and so on, so that I arrive at the overall dependence. Okay. The rest of them are, I think, of order unity. I'm tempted to say, I need to check. I've completely ignored overall factors that can be found in the text. Okay. If you do this analysis carefully, you will be able to fix those factors. So what do you have? Rho PBH naught divided by rho C naught. Okay. Rho C naught by rho CDM naught. Right. And I'm just rho nr naught, right? And so what is this? I'm going to take this here. So this is rho PBH naught by rho nr naught, okay? And I have rho nr naught, okay? I have accounted for this, I accounted for this by C naught, rho C naught, okay? By rho CDM naught by rho C naught. I can multiply by h squared, I can multiply it by h squared. So this is omega nr naught and omega CDM naught h squared, okay? That we know. Now, what is this? Rho PBH, this is equal to, okay, I'm just going to, this is a constant. Remember, constants I'm going to ignore, okay? What is this? This happens to be rho PBH at equality divided by rho NR at equality. Why so? PBH essentially behaves like non-relativistic matter, and therefore they all have, both have 1 over A cube. So I can evaluate at any epoch I want. All right. So what do I have now? Okay. Now, this is proportional to FPBH naught is proportional to rho PBH of K. Okay, I'm retaining the NR equality, just right? Rho PBH at the time of formation, okay, and it is diluted to A by A equality. This is AK by A equality Q. That's all. Okay. Now, remember, what did I define? Okay. What did I define rho PBH of K as? Rho PBH is this fraction beta of M times rho total at K divided by rho NR at equality, okay, AK by AEQ whole cube. Okay. All right. Now, rho NR at equality is modulo factors of 2 is rho radiation at equality, rho R at equality. Correct? Okay. And therefore, this is, I hope you understand, this is like A equality by AK power 4. Okay. All right. So what do I get? I get this is A equality by AK. So in other words, FPBH naught, if I want a function of M, is proportional to beta M times A equality by AK. Right? Okay. And, but AK by A equality is M power half. Okay. Is M power half. I'm sorry. It is AK by A equality is M power half. This is M power minus half. Okay. Actually, modulo all the constants that will appear, this is the result. Okay. This M power half, it should appear in all the equations I've written. Somewhere you should be able to locate it. Okay. So modulo constants, okay, you will find that this is M power half. It's usually written in terms of solar mass. Okay. And what you typically find is that if you have enhanced power, okay, there is a 1-to-1 relation between K and M, as I have indicated, right? You just need to plug in those numbers. I ignored all the constants. You need to plug in those numbers to understand what is the relation between K and M. M was K power. M was K power minus 2. Okay. You need to, so, and K was 1 over R. All right. So there is a 1-to-1 relation. So if there is a K peak, you expect the corresponding M peak. You can arrive at from that relation. And if you have power which corresponds to scalar power at the peak scale is of the order of 10 power minus 1 or so, look at the plot of the power spectrum in ultra slow roll that I had plotted yesterday at the very end. Okay. And I had said it's like 10 power minus 1 or so. you can have FPBH of naught close to 1. It depends on the value of delta C, which I haven't had the time to comment about. It's crucially, extremely sensitive to delta C. For 0.3 or something on the lower end of the of delta C that is often considered, you'll find that FPBH can be anything between 10% to 1%. FPBH naught is 10 to 1, is of 0.1 to 1, which means it's about 10% to 100% of the cold dark matter density today. Okay, so I think these estimates are correct. Let me emphasize for the case of the primary gravitational waves and primordial black holes, my estimates are correct. Okay, the arguments are correct. You need to fit in all the details. In the case of reheating that I talked about earlier, there are a few steps I've ignored. Okay, I missed out, and therefore I could not present the derivation logically within the finite time available to me. But all the steps are there. I will update the list of references, and these new references will include discussions on these topics that I have discussed, that I've described over the last 3-4 lectures. Okay, and unfortunately, I could not discuss secondary gravitational waves, and I will stop here. I'll be glad to answer questions. Yes, Fazil.
So I have a question about this smoothing scale that you told.
Please say that again.
The smoothing scale.
Right.
So I understand that this is something like the maybe the beam size of my instrument or something like the resolution of the simulation box, etc. Right? So what exactly is it doing inside this thing, or how do we estimate the smoothing scale?
Well, we don't have. That's what I said, right? I finally set the smoothing scale R to be essentially K inverse.
Okay.
Okay. So in that sense, so you have matter which is collapsing, and I want to smooth over a certain scale. Okay. Sometimes the so-called top hat window function is used to estimate the amount of mass that is formed inside. That's what it is.
Okay.
Okay.
Yeah, I'm confused about, can we use linear theory here since black hole formation is a non-linear process, no?
Absolutely. Once it's inside, there are other effects that can play a role, non-linear effects in the process of formation when they are inside the Hubble radius. Okay. Until re-entry, I see no issues. Until re-entry, whether linear theory is valid until that point is another question. Well, you can have non-Gauss entities generated during inflation because of deviation, strong deviations from slow roll, and those non-Gauss entities can affect the formation as well.
Okay.
So yes, one need to carefully take into account the non-linearities. So there are two non-linearities. One is when they are inside the Hubble radius and that evolution, and the non-Gauss entities generated when the primordial spectrum itself is generated.
So in the integral, that beta, we calculate this delta is going from some critical density to correct. 1, right? So 1 means it's in the
yes. I mean, you can anything above will form black holes. That's the assumption. Okay, that will collapse to form black holes. That's the assumption.
Yeah, usually in the astrophysical case, there used to be mass limit, like Chandrasekhar limit or something, to form black holes, right? So here,
you need to here. Look, I am not on top of the literature on this. Okay, there are more sophisticated discussions in the literature where they say it will even depend on the power spectrum itself. Okay, as to what is the criteria for black hole formation is something that is open. It's not completely understood. It is being discussed as we speak. There are papers by, for instance, Cristiano Germani and Ravi Sheth, where they discuss, how the shape of the power spectra will decide the criteria for formation. I do not know all the details.
Okay. So another question, is there any possibility of forming other kind of compact object like,
Oh, I
black
think that
hole?
is you're asking me a question which no, I am not, maybe black holes seem easy to consider.
Thank you.
There are works that consider enhanced power and associated formation of something called ultra compact mini halos.
Okay.
And one can put constraints on PS based on those as well.
But they are compact, but not black holes.
Yes, not
Okay,
necessarily just black
So there
holes.
lies your answer.
And I think even in light of JWST's discovery, there are groups in
I know.
IISc that try to enhance power, but not necessarily form black holes, but just form more abundant structures.
Yeah, for instance, there is another scalar field called axion field. So you can form, it can induce some kind of topological defects, and it can then form like.
So to my understanding, the details of what happens once these things, fluctuations enter the Hubble radius is non-trivial. I do not know whether it is completely understood. I have seen the title of this paper you mentioned, but I do not know what stops it from becoming a black hole and remain a compact object.
No, like the Jeans length of these objects.
Right.
It depends on like this Jeans instability, right?
Okay.
Black hole formation. So these are sort of in the oscillatory regime. These are not a Jeans unstable object. That's why you don't form black hole.
Okay, you don't end up forming
Yeah.
black
So
hole. Okay.
one of the object is axion mini cluster.
Okay, you are better placed to comment about it than I am. Yeah. Yes, Avi. Can you speak into the microphone?
The fraction of the mass inside the Hubble radius that actually collapses to form black hole when the K mode enters the Hubble radius, that gamma of course depends on delta critical, right?
Say that again.
That gamma depends on delta C.
That gamma depends on the equation of state of the background, during at the time when it re-enters, etc. Okay.
Okay.
That's what it is, right? Gamma does not depend on delta C. It depends on essentially, it has some relation to 1/3. Okay, the equation of state. You could have considered a scenario where they re-enter during the epoch of reheating and forms PBHs. Okay, if I recall correctly, gamma depends on that.
Okay.
And it doesn't depend on delta C.
And are we only considering those K modes which are entering during radiation domination, not after?
For simplicity, otherwise my algebra is extremely messy. Okay, so I have ignored epoch of reheating. Okay, but you can do that and calculate what happens when they re-enter during the epoch of reheating. You may have some modes which re-enter in the power. Okay, some modes which enter during reheating, or some modes which enter during radiation domination, or if it's a sharp peak, all of them may enter during the epoch of reheating itself, and you just have to repeat those arguments assuming they enter during the epoch of reheating.
Yeah. Okay. And even some K modes are also entering right now because as our Hubble radius is increasing, so still the formation of PBHs is going on.
So they are entering today on those are CMB scales. We know that power is not significant on those scales. Okay. Now, whether they will collapse to form black holes, they will collapse to form structures. Okay. You need very large power, enhanced power to collapse to form black holes.
Yeah. You mentioned.
And the power on those scales we know is well constrained by the CMB data.
Okay.
All right. Are there questions online, Radha? Okay. All right. Okay. Sure.
We discussed about the Starobinsky and alpha attractor inflation models. So how does these different models, this beta parameter for these models, how much it differ as it?
Which
Th-
this
this-
beta
yeah,
M.
that
But
that
those are
attempt.
flow roll models, right? Okay, so beta of M
Right,
will
right.
be extremely small.
I see.
Okay, any slow roll inflationary models will lead to very small values of beta FM, FPBH of 0. Yeah, I'll come to that. I realized that as well. If that is why I was commenting about slow roll models, not Starobinsky model. So in slow roll models, this will be very small. Okay, it'll be much smaller than even 10 power minus 10 and so on.
Yes.
Okay. There is one Starobinsky model. There was another Starobinsky model where we discussed there was excess power. Okay, that leads to a wide ending inflation is a problem. But such scenarios, if you have enhanced power and end of inflation, okay, and then the standard story comes through. If your power is like 10 power minus 1 or close to that, okay, you'll have a significant amount of VH formation. And the mass of the black hole will depend on where the peak lies.
Yeah, so
Did I answer your question?
yes. So I was asking like the power spectrum peaks at one particular value for these models like mostly, or as in we get different peaks, like peaks in different cases for.
So that depends on your inflationary model. You can tweak the parameters of your model and move the peak to some extent.
Okay.
Okay. So there is something I need to mention, but this gets too technical. Okay. So what essentially happens is as follows. We talked about power spectrum, which is nearly scale invariant. There is a rise and there is a fall like this. Okay. And there is a dip too here. We talked about this. And this is 10 power minus 1. And this is 10 power minus 9. Right? PS of K. And now, let us say I have smoothened this. This is your K peak. Okay. Often what happens is that if you try to bring this peak close to CMB scales, it affects the NS here. R is a different matter. It severely affects the NS. In fact, there are very few single field models, okay, where NS is close to 0.96 at the pivot scale. And you have a rise which is sufficiently large, like it goes to 10 power minus 1. Okay, you need fine tune. We can reconstruct such scenarios. Raghavendra has done that, but they are somewhat artificial. Many of the single field models have this problem. Okay, as you bring, if the peak is farther away, NS is close to can be close to 0.96. Okay, but if you bring NS, the K peak smaller and smaller, say, as I already mentioned how the K peak has to be greater than 10 power 4 or something. Okay, to ensure that spectral distortions are not, constraints are satisfied. Okay, so if you bring close to 10 power 4, 10 power 5, then the NS is severely affected. Then you can go to two field models and generate such features. Okay, I hope I answered your question.
Yeah, thanks.
So, and the model will allow, some tuning of the location of the peak, but as you bring it closer to the CMB scales, the NS is affected significantly. Okay, Radha? All right. Thank you, everyone.
Okay. So this brings to close exciting Vignyana Patashala series of lectures. I'm sure you guys enjoyed it. I could make out even just from the numbers of people coming around. And so it's my privilege and pleasure to warmly thank Sriramkumar for taking this effort to conduct this course. And I hope many of you will find that useful in your research or, at least in the perspective you have about the early universe. And feel free to stay in touch. Sriram, Raghavendra, his gang, I can see another member of his gang there. And so, and in general, and at RRI, we hope to have many such schools across other disciplines also, but including astrophysics. And I hope to see many of you here. And I'm really glad students from in other institutes. This has been always something that I thought was a very strong point of Bangalore. And long back, there used to be something called a neighborhood astronomy meeting, which was talks. Now there is some kind of a conference that happened last year, like 3-day workshop or something. But, a lot of people also mentioned that I should take up and start this. But these are student driven. Inherently, if students want to get together, do things and put up a demand, at least at RRI, we would try to, if you find a great lecturer and you say, okay, please conduct a set of lectures. If we are not short of, timing or something, that we're most welcome to do that. And if you want Sriram to give you another set of lectures beyond primordial black holes, I'm sure. Right?
Yeah, we can think of something.
Yeah, or something else. Okay, great. So with that, let us all thank Sriram for his effort.
Thank you.
And and also thank you all again for coming and oh. Yeah. This is the biography of Raman.
Thank you.
I don't know if you read it.
No, I have not read
No,
it.
this
Thank
is-
you very much.
I'm told it's one of the
Good.
good ones and very well regarded.
Okay.
So I'm sure you enjoy. And yeah, so till next time, and please feel free to visit RRI on any occasions. I'd like to see a lot of flux of students coming back and forth from far-flung IIA, ICTS. But, I think the numbers are same even from close by ISC. So anything we can do to make it happen, please let us know.
Thank
Okay.
you.
Thanks, Sriram.
Thank you. Thank you. Pleasure.
Good. All right, so you have the chalk.
Yeah, chop. Thank you.
Warriors used to have the tilak, so teachers have a chalk.